I reduce the proof of the parity statement about ranks of Selmer groups to the existence of a certain higher dimensional version of the Castle state pairing. So in the remaining 2 lectures, I will try to sketch the outlines of some general theory of duality for Galois modules arising, for example, in Iwasawa theory. You can find more details in my preprint called Selmer complexes. I like to think of that paper as something like EGA1 for Iwasawa theory. Today I'm going to speak about duality for Galois cohomology. No Selmer groups today. So what I'm going to do is just to repackage the well-known duality theorems due to Tate into a fancier language, which will then be useful if you want to construct those high-dimensional pairings. So the notation is as before. F is a number field. S is a finite set of primes containing all primes dividing P and infinity. Well, we have the Galois group with respect to ramification. We also have the corresponding local Galois groups, GV. We have a ZP module T, which is free and has a continuous linear action of this global Galois group. Well, in fact, I want to treat simultaneously the local and the global case. So I will have something with an action of G, and G will be either this global Galois group or local Galois group. And so as before, we can associate to T all kinds of other Galois representations like T star, which was, remember, the ZP dual of T. This is again compact. And then we had the discrete modules. We had A, which was T tensor QP over ZP, and the corresponding A star, which is T star tensor QP over ZP. So today we'll just do some linear algebra, I'm afraid. So this is, of course, isomorphic to the Pontryagin dual of T star. This hat, or chapeau, is the Pontryagin dual. Similarly here, this is isomorphic to the Pontryagin dual of T. So what does the local duality tell us? We've seen this before, several lectures. So now I will take for G this local Galois group, GV, the absolute Galois group of the completion of F at V. Now, so usually this is stated for finite modules, so we can reduce the general statement to finite modules. So if you take the finite module T modulo P to the nt, then if you take, on the contrary, P to the n torsion in A star, so they are naturally Pontryagin duals. Yeah, so the Pontryagin dual of this is naturally P to the n torsion in A star, and similarly for the other pair. And so this means that Tate's duality tells us that if you take Galois cohomology Hi of, say, this module T over P to the nt, this will become, so under Pontryagin duality, this will be Pontryagin dual to H2 minus I of the corresponding module here, A star P to the n, with a Tate twist. So this is the Tate duality for, so this is Pontryagin dual. For finite modules. Now one can pass to the limit in an obvious way. You can take the inverse limit on the left-hand side, and this will be Pontryagin dual, of course, to the direct limit of the things on the right-hand side. So what you get is, again, a Pontryagin duality between Hi of T, which is now a compact thing, and H2 minus I of A star 1. So we should be discrete. And similarly, for the other pair, you get here Hi T star 1 and H2 minus I of A1. So this is completely automatic, given the, yeah?
Is there a 1 on both?
Ha ha ha. Thank you. That's correct. So this is completely automatic, given the functorialities. Can I get rid of this? No? So the question is whether one can find a similar relationship between the corresponding cohomology groups just for the compact modules. So what is the relation between the cohomology groups of T and the cohomology groups of T star 1? What's the best way of formulating or possibly proving such a relation? So the way I like to formulate this is to repackage everything into a very simple picture. So let me just remind you of something completely elementary, namely the duality for ZP modules. But in fact, I want to also talk about the duality for complexes of ZP modules as a basic example of the channel theory. So we have those Galois representations. We have T, we have T star. Let me ignore the Tate twist. So I'm ignoring the Galois action now. I'm just looking at the ZP modules. So then we have A and A star. So how can we relate them? So there are all kinds of arrows in here, which are fairly easy to write down. So what are these arrows? So the horizontal arrows, these are just ZP duals. The diagonal arrows, well, these are Pontryagin duals, but since we are talking only about ZP modules of finite or cofinite type, these are just the Holmes with values in QP mod ZP. And finally, the vertical arrows are just tensor products with QP mod ZP. So this is the relation between the coefficients, apart from the Tate twist. So morally, the relation between the cohomology groups should be essentially the same. Now this is certainly true for the diagonal arrows, when you have again Pontryagin duality for those cohomology groups, but it's not true for the other ones for the simple reason that so this functor is exact, so it really commutes with all kinds of cohomology because QP mod ZP is injective, but those two are not. And therefore, when it comes to cohomology, one also has to take into account various derived functors. So the correct way of looking at this picture is in fact replacing modules by complexes and these functors by their derived versions. So this extends to not necessarily free modules, non-free ZP modules T, and in fact to complexes of ZP modules as follows. Well, maybe with some finite conditions on cohomology. So we have the same kind of a diagram. I want to call those arrows names. So the diagonals will be usual D, the horizontal arrow will be script D, and the vertical arrows will be called phi. So now if I want to do this for complexes, I must take the derived versions of these maps. So first the easiest one is the diagonal arrows because, as I said, QP over ZP is injective. So if I take now some complex here, I just have to take the corresponding complex of morphisms into, well, again, into QP mod ZP. Now, what about the horizontal arrow? Well, we have to do the same thing, but as usual in this yoga, we must replace ZP by an injective resolution. So there's a fairly canonical injective resolution, which is QP goes to QP mod ZP. So this is a complex this is in degree 0, this is in degree 1. And this thing is an injective resolution of ZP. Yeah? And similarly, for the vertical arrows, we must take the derived tensor product, therefore replace QP mod ZP by flat resolution. So phi of some complex will be the tensor product with, say, the following flat resolution. Just zp goes to qp. Now this is in degrees -1 and in degrees 0. Because this is a flat resolution of qp mod zp. So this is what happens on the level of complexes, but of course one should really write these things properly using the language of derived categories, which I will recall in 2 seconds. So somehow the fancy way of writing this really is to say that this curly D is just R hom into Zp. Phi is the derived tensor product with Qp over Zp, and D is R hom into Qp mod Zp. In fact, here one can forget R because Qp mod Zp is injective. So what do these letters R and L mean? Well, if you haven't seen derived categories before, don't despair. This is just a language how to express the fact that one should really work with complexes rather than with their cohomology, because they contain more information. So instead of talking about derived functors like xt(i) or tor(i), one should really talk about the whole complex which computes them. So let me just make a 2-minute digression about the language of derived categories. Now, so you can pass for an expert if you just drop everywhere 2 key letters, R and L, right? So in all the formulas, that's how it works. So for example, the derived category of the category A modules, where A is some ring, what are the objects, what are the morphisms, and what are they good for? Well, so objects, they are represented by complexes of A modules. And somehow the idea is that in the derived category, 2 different injective or projective resolutions should be, in some sense, canonically isomorphic. So there should be no difference between them. That's the whole idea, right? So morally, so if the classical attempt of making this precise is the following. Maybe it's not the best one, but it just says that a morphism of complexes inducing an isomorphism on cohomology this is what people call a quasi-isomorphism, becomes an isomorphism into the derived category. Becomes an isomorphism into the derived category. Well, the reason I put the star here is that you can put some extra conditions on the complexes. Maybe they are half bounded or bounded or something like that. So this really means that, and the derived category in some sense is the universal object satisfying this. This doesn't quite mean that if 2 complexes have the same cohomology that they are isomorphic, you really need some kind of a map or between them. But in fact, what happens is that a morphism in this derived category is represented by a picture like this. So you really want a morphism, but this is not quite represented by an honest morphism of complexes, but you have another complex x prime, a quasi-isomorphism here, and an honest morphism in here. So that's the usual situation. You localize your category. You invert all the quasi-isomorphisms. But somehow on the operational level, what really matters is that one doesn't speak about those derived functors on the level of cohomology, but on the level of complexes, and therefore reasonable functors should always induce their derived versions between derived categories. And so those corresponding derived functors are computed, well, can be computed, using resolutions, usually. So this is just a language, like the language of schemes. If you write spec of A, it doesn't really matter what it means if you know how to manipulate them. And so the same thing is happening here. You just replace all the objects by the appropriate resolutions, and it works. It's just a lingo. All right, so we have this picture for complexes of ZP modules. But now we need some Galois action and maybe some cohomology. So let me get back to Galois representations. So how can we restate some well-known facts using this language? So as before, we have our group G, either the global or the local Galois group, or in general you can do this for any profinite group if you wish. And then we have our representation T as before, so we define A as before, but also V. Remember there was V, which was T tensor QP. This was a corresponding QP vector space, and then we had the usual exact sequence TVA. So I apologize, today's talks will be just linear algebra, all right? So in this situation, A is discrete, so there is automatically a continuous section, and therefore there is an exact sequence of continuous cochains, where continuous has an obvious meaning. All the three modules have an obvious topology, and G has the profinite topology. And so since this has a section, we have also a 0 on the right here. Anyway, A is discrete, so there's no problem. So how can one rephrase this in terms of those arrows I've introduced before? Yeah, so these are continuous complexes of continuous cochains. So what does it mean in terms of our functors? Let me recall that phi was this functor which was the derived tensor product with QP mod ZP. So for example, this means that phi of T is the complex T goes to V, which is of course quasi-isomorphic to A. So phi of T is A. Now, what does it mean on the level of complexes? Well, if you look at phi of the corresponding cochain complex, you do the same thing. Right? You have to tensor with, not with QP mod ZP, but rather with this complex ZP goes to QP. That's the flat resolution. And this is what we've done here. We've tensored T with this complex, ZP goes to QP. So let's do that now with the corresponding cochains. So this will be, well, you get two complexes. So you have the complex of cochains for T, then you have the corresponding complex tensored with QP. So you have two complexes, then you have something like the total complex. So, well, I want to something like the co-kernel or the total complex. So this is known as the cone in the trait. Cone is something like the co-kernel. But now you see, just by definition, essentially of this continuous cohomology, these are just continuous cochains because G is compact with values in V. And the cone, as I've told you, is a co-kernel in the situation where the map is injective. And so this exact sequence tells us that it is naturally quasi-isomorphic to the co-kernel, which are the continuous cochains with values in A. So in the derived category, there is a canonical isomorphism between phi t and a, and phi of the corresponding cochains again. So this really means that the existence of this exact sequence, which is very easy, is equivalent to the fact that cochains commute with this functor phi, so automatically in an appropriate derived category. So the upshot is that in the derived category of ZP modules, taking continuous cochains commutes with phi. So I want to give a name to this complex, rather to the corresponding object in the derived category. So as I've told you, every complex represents an object in the derived category. It's just that morphisms are different. So let me call the object of the derived category, say, ZP modules represented by the continuous cochains with values in T will be called R gamma G with values in T. Yeah. So this is how you, as I've told you, all you have to do is to drop those letters R and L all over the place. This is just a notation. There is no content whatsoever. The cohomology of these things are just continuous cohomology groups. And the point is that one should manipulate those complexes to get some quasi-isomorphisms between them. So how can one reformulate Tate's local duality in this language? So now G is this local Galois group. And I start with, I have T, T star, A, and A star as before. Yeah. Now I can take their cohomology. So here I have the corresponding continuous cochains with values in T. Here the continuous cochains with values in T star with the Tate twist. Here I have the corresponding objects for the discrete modules A and A star 1. So, as I've told you, this, if you apply phi to T or to T star, you get the corresponding discrete modules, and phi commutes automatically with continuous cochains. Therefore, phi takes those compact complexes into the corresponding discrete complexes. Now I would like to say that Pontryagin duality interchanges these modules. This is almost true, except there's a shift into dimension, because one has to shift everything by 2. So what does this notation mean? Let me recall that if you have a complex X, if you shift it by n, then the component in degree I is just the component in degree I plus n in the usual complex. So you have to shift by 2 to the left, and then this will really be true. So let me just check. So why is this true? So we've seen that this diagram really holds, that this is all right for the horizontal, for the vertical arrows, that phi commutes with taking cohomology. Now what about the diagonal arrows? Well, we know that, so D is the Pontryagin dual, and we know that the Pontryagin dual of Hi of T, this is Pontryagin dual, is by Tate, this is H2 minus I of A star 1, which is H minus I of this complex R gamma A star 1 2. So this is So this shift 2 just means the 2 is the same 2 which appears in the cohomology. So since we know that we get isomorphisms by applying the diagonal arrows, we get also an isomorphism by applying the horizontal one, which gives you the desired relation between the cohomology of those compact modules, except that it's a relation for the whole complexes. So if you want some relation on cohomology, you write some spectral sequence, which in our case really boils down to an obvious exact sequence, which everybody should know. Exercise. Right, so this is just a way of reformulating the local duality. Again, there's nothing new in here. Right? So all the work had been done by Tate and I think by Grothendieck, who introduced the derived categories. Now, how does this work in the global case? So in global duality, so this is Tate Poitou. Yeah, in fact, I should probably perform my usual trick, which is just to make some local replacement, not the global replacement. All right. Well, now I think I have to introduce one more object because, as everybody knows, in the Tate-Poitou duality, one doesn't quite get this. So one needs one more object. So before I state the result, I need one more object. One needs co-chains or cohomology with compact support. So in this case, the group is the Galois group with restricted ramification, which acts on T. And so we define those co-chains with, well, continuous co-chains with compact supports, say for T or for any other module. How? Well, so we should take, so we have the global co-chains for the global Galois group, and we can map them to the direct sum over all finite places in S of the corresponding co-chains of local of the local Galois group. So this is, we have two complexes. I would like to take something like the total complex, but now I want to take something like the kernel. So this means that I have to take the cone of this and shift it by -1. So this behaves like a kernel. So what does this mean? This means that we have something like a short exact sequence where this is on the left, this is in the middle, and this is on the right. Also, it's called a triangle, not an exact sequence. So let me denote by R gamma C the corresponding object of the derived category, corresponding object in the derived category of ZP modules. And so because we have this triangle, there is a cohomology exact sequence where you have HI compact support, maybe with T, then you have the usual cohomology, and then you have the sum of all the local cohomologies. And then you have the cohomology with compact support in degree HI plus 1, etc. Yeah? And these objects appear, of course, in the Poitou-Tate duality, but the right way of looking at them is by introducing this complex of coach. Yeah?
The SF, is that all the places of F or just the finite places of F in our set S?
Well, I had this assumption which said that if P is equal to 2, then there are no real places. SF is S minus the infinite primes. And I also have this assumption that if P is equal to 2, there are no real places because I was lazy. If you don't have this assumption, you have to add some small piece with Tate cohomology, with the full complex which also has negative degrees. All right, so with this notation, what is the Poitou-Tate global duality? Now we have this global Galois group. We again have those four representations, T, T star, A star. So on the one hand, we have the usual cohomology. On the other side, we need to take the compact cohomology with compact support, and now the duality has something to do with degree 3. So now this will be the corresponding
subscript D. And the G.
Ah, yeah. That's entirely correct. So let me just keep G, okay? It's this G. All right, so this is now the corresponding statement of the global duality. And with the same proof, because we know that the usual and also the cohomology with complex support commutes with phi, the Poitou-Tate duality gives you these isomorphisms for the diagonal arrows, and therefore we also get the same relation for D. Although, strictly speaking, one has to produce first an arrow and only afterwards prove that it's an isomorphism. But this is a technical detail. All right, so this is just a repackaging of the usual theory. How can one get from this some duality results in Iwasawa theory? Again, what one has to do is to pass to a limit in an intelligent way. So how does it work? So we are still in the global situation. Now we have some extension f infinity over f, such that this Galois group, which are denoted by gamma, is isomorphic to zp to the r for some r greater than or equal to 1. So this implies automatically, this f infinity is automatically contained in what was called fs. It's ramified only at primes dividing p. So as before, I have T a representation of GFS. So I write f infinity as a union of finite extensions f alpha. So f alpha has finite degree over f. And I'll denote by gamma alpha the Galois group of f infinity over f alpha. So as usual, we have the Iwasawa algebra. So lambda is the completed group algebra over Zp of gamma, which is by definition, the projective limit of the group algebras of gamma over gamma alpha. So as a ring, it is isomorphic to the power series ring in R variables over Zp. Non-canonically. Right? Sorry. Yeah. Thanks. So how can we deduce statements about cohomology in this Iwasawa setting over f infinity from the things over f? Well, there's a well-known device in group cohomology which is called Shapiro's lemma. So let's try to apply it scientifically, right? So how does it work? Well, so we work over those finite extensions of alpha, then we want to pass two suitable limits. So let me first do it for discrete modules. So how does this work? Well, so we have those modules A and A star. And so we can look at the corresponding cochains now over F alpha. So we have the same Galois group with the same ramification set of ramifications. So this will now be the Galois group of Fs. This doesn't change over F alpha. And now for this discrete module A. So this is the usual cochain complex. So I don't write continuous, although it is continuous. And so the Shapiro's lemma gives you quasi-isomorphism with the complex over the base field F, but now with the induced, or maybe it's co-induced, I never know which one is which. So you take the Holmes from the group algebra of gamma over gamma alpha with values in A. So this is the induced module. And so this quasi-isomorphism commutes with restrictions. Which means that one can pass to the limit brutally. So we can take the inductive limit with respect to alpha we obtain a quasi-isomorphism, so between the cochains. Well, here I have this corresponding group over F infinity. What is this? This is the Galois group of Fs over F infinity. So we get Shapiro lemma gives me a quasi-isomorphism with now the cochains over F with the module which I want to denote by F gamma of A, which is somehow the limit induced module. Let me write down the formula for this, where, okay, so what is this F gamma A? So where if you pass to the limit, you get ZP homomorphisms which are continuous from lambda to A. Because here lambda is the limit of these things. And I also remind you that A, this was the Pontryagin dual of T star, so these were homes ZP from T star into QP mod ZP. So let us now play with two different homes, the usual games. So by adjunction, this is the same thing as homes ZP from T star into continuous homes from lambda to QP over ZP. And this is the Pontryagin dual of lambda hat. And so again, by adjunction, this is the same thing as now lambda linear homomorphisms from T star tensor lambda over ZP into lambda hat, which is what I want to call d lambda of this module T star tensor lambda. What is dl? Well, dl is just a lambda Pontryagin dual, except I look at this as a lambda linear object. So here I put, first of all, d lambda of any lambda module to be the homes into the Pontryagin dual of lambda. And this is the Pontryagin dual for lambda modules of finite or cofinite type. This is just my notation. And another piece of notation is that I want to denote by R gamma of Fs over F infinity the corresponding object in the derived category represented by this complex. Yeah? So this will be now the object of the derived category of lambda modules represented by this cochain complex of this induced module. Now the cohomology of this object, so hi of this complex, are just the inductive limits of the cohomology groups over those layers. Sorry, of A. Yeah. So this is just a notation. And I can do the same thing now with the compact modules, T and T star. So how does this work? This is slightly more complicated for the following reason. So again, you have this quasi-isomorphism given by Shapiro's lemma. Now I take the module which is, I think, co-induced, which means that I take the tensor product with the group ring, because I need the other functoriality of this construction. I was taking inductive limits, now I want to take the projective limit with respect to the co-restrictions, but the point is that this does not, first of all, if you want to define co-restriction maps on those cochain complexes, you need some choices. You have to choose some coset representatives. So the co-restrictions are not uniquely determined. And second, even if you make those choices, then you don't quite get compatibility, only compatibility up to homotopy. This is the usual situation in this business. So this commutes with co-restrictions only up to homotopy. But we don't care very much, because after all, we care only about cohomology. So we want to take some projective limit, and it's on this side where the projective limit will be more pleasant. Okay? So taking the projective limit, we see that the cohomology groups of, now I take the cochain of the complex of continuous cochains. For this, now I take the projective limit of these for an obvious maps. So I take now projective limit of these things. Which is what I want, which is just T tensor lambda, which I want to call script f g of t. So I'm in the middle of a sentence, so the cohomology of this complex of continuous cochains with values in T tensor lambda so these cohomology groups are just projective limits with respect to co-restriction with values in T. Now here, so the point is that there are no derived functors of the projective limits because of finiteness results of these cohomology groups. One doesn't have to worry about anything now. And this group is denoted by the French school H.I. Iwasawa, the Iwasawa cohomology of T, the projective limit of these cohomology groups along the tower. So let me call it Iwasawa cohomology for this tower with values in T, although it depends on S, so this notation is completely wrong, but Iwasawa cohomology. So if you want some information about this, all we have to worry about is this complex of cochains. And so let R gamma Iwasawa be the corresponding object of the derived category, be the corresponding object of the derived category of lambda modules. So this has cohomology of finite type, while the other one has cohomology of cofinite type. Okay. Now, so what's the relation between these things? So we started with T, which gave rise to other representations, A star, T star. So what's the summary? So we start with the picture we had before. We had T, T star, A star, and the relations between them, as before. Here we have those functors. And now we have those induced modules. So we get, here we get the corresponding tensor products for the compact things, and here we get the induced modules, the Hom for the discrete ones, and also on the other side, the same thing for the starred objects. And now I claim that there's the same relation between them using the similar functors over lambda. So I put subscript lambda everywhere. I've already defined the diagonal arrows, except this is not quite true. There's the action of this standard involution I. What do I mean by this? So first of all, No, I didn't have twist here either. It only comes in the cohomology because... Yeah, so my star is different from your star.
Yeah, okay.
Because the state twist really comes from the dualizing module in the language of SAR. That's a separate thing. This construction is before actually taking cohomology. So what is this business of the involution? If I have some lambda module m, let me, the usual notation mi is the same module except that the lambda action is twisted by the standard involution. And I repeat that I is the standard involution of lambda, which is induced by the inverse on the group gamma. So I from lambda is given by I of gamma equal gamma inverse for every little gamma and capital gamma. So why do we have it here? So what were the formulas once again? So f gamma of t was t tensor lambda with the diagonal action. So what is the action on lambda? Remember, by construction g fs surjects onto gamma, and this in turn embeds into invertible elements of its group ring. So this gives you a canonical action on lambda. So essentially that's the action here. Maybe it's inverse depending on how you normalize things in Shapiro's lemma. And yeah, and similarly this f gamma a was this Hom continuous Homs from lambda to a. So where does this I come from? You see, the point is that if you define something like the dual, say this Pontryagin dual or the lambda linear dual, then the conventions for the lambda action and for the gamma action differ on the dual exactly by this. So the point is that the conventions, not just conventions, I think these are correct rules. For lambda and gamma actions on dl on anything differ exactly by this involution. So that's why those involutions appear there. Well, it should come as a no surprise. All right. So I've defined those vertical arrows, sorry, the diagonal arrows. Now I have to define the horizontal and the vertical arrow. So what's the horizontal arrow? So this again the derived, this is the derived Hom, the derived lambda linear Hom. What does it mean? It means that I have to replace lambda by some injective resolution. Well, there is in fact a relatively canonical, well, fairly canonical resolution in this case. So there is, so this is the analog of the resolution QP goes to QP over ZP. Yeah, you should think of this as a basic example. So what is the analog for lambda? So that one builds this up from what people call the injective hulls of various residue fields. So you take the sum over all prime ideals of height 0, then you take I of p. I'll explain in a second what I mean. You go all the way to prime ideals of height d. D is the dimension. I'll write down everything. So what kind of a complex is it? So this will be in degree 0. This will be in degree d, which is the dimension of lambda, which is r plus 1. And so this is an injective resolution of lambda. What are those IPs? IP is what is known as the an injective hull of the residue field. So in this case, for DVRs, we get exactly this absolutely canonical thing. So for example, the injective hull of the maximal ideal is exactly lambda dual. Sorry, I mean the injective of the residue field at the maximal ideal. Oh yeah, this is my notation. Okay, sorry. Yeah. Now this works because lambda is Gorenstein. Such a thing exists for every Gorenstein local thing. All right, what about the vertical arrows? So let me keep this diagram here. So now we need some analog of this for the vertical arrow. We need some adjunction formula. So usually you have an adjunction formula between hom into x tensor yz into hom into another hom. So the only thing one has to do now is to drop the derived functors everywhere. So there will be L here and few R's everywhere. Maybe there are some assumptions on those complexes, but they will be always satisfied in my case. So I want to apply this for y equal to z equal to this Pontryagin dual of lambda. So what do I get? So on the left I get the Pontryagin dual of x and the derived tensor product with lambda dual. And on the right hand side I get precisely this horizontal arrow. This is called the Grothendieck dual, by the way. And so in order to have this commutative, I'm forced to call this derived tensor product phi lambda. So this is exactly the analog of what's happening over ZP. Okay, so I have all the arrows. Now, just to assure you that things worked well, let me write down an explicit flat resolution of lambda, of the Pontryagin dual of lambda. There is a finite flat resolution in the same way that lambda had a finite injective resolution. So let me fix some elements x1 up to xd in the maximal ideal such that the quotient by the ideal generated by them is finite. So this is what people call a system of parameters. And then you can actually write explicitly this functor phi L on the level of complexes as a tensor product with the following flat resolution. You take the sum of all the localizations at xi's, then you take the sum of all the localizations at the double products xi, xj, and you go all the way until the localization at the product x1 up to xd. You put this at degree 0, therefore this will be at degree minus d. Remember, d is the dimension of the Iwasawa algebra. Now for the people who know what's going on, this is isomorphic to the complex computing local cohomology shifted by d on the derived category of lambda modules with finite type cohomology. So this is the right way of looking at this. And therefore this diagram here is just this is a compressed way of writing down three duality theorems. There's Pontryagin duality, there's Grothendieck duality, and the commutativity here is what people call local duality. Okay. So I want to convince you that one has the same properties as for over ZP, in other words, that continuous cochains commute with phi. But of course, if you write phi in this way, you get those localizations, so you must define the corresponding cochains. This works. So how do continuous cochains work in this situation? If you have some non-zero element of lambda, and if you have your profinite group G acting on you have some module lambda module m acting upon G. So here m is lambda module of finite type. Then if you want to compute the phi L of m, you have to write down the complex which has entries m tensor various localizations of lambda. So one needs some sensible definition of the continuous cochains of this. So one way is to, well, this is wrong what I'm going to do now. So one would like to somehow define this as the corresponding localization of the continuous cochains of m, except that one have to prove that this really depends only on this. So the correct way is in fact define the left-hand side and then prove that it's canonically isomorphic to the right-hand side. But it works. So this really makes sense and makes the left-hand side well defined. And after this, everything makes sense, and then phi lambda will commute with everything. So phi lambda of the continuous cohomology with m will be canonically quasi-isomorphic with the continuous cochains with values in this phi lambda of m, and this will be true not just for one m but for complexes of m's, which is what one needs. And similarly for continuous cochains with compact supports. All right, so now all one has to do is just to look at the diagram and write down the corresponding thing for the Iwasawa cohomology. So I'll just do that. And I'll stop in something like 4 minutes. So what's the duality for Iwasawa cohomology? So we just take those big representations, take the corresponding continuous cochains. Let me just write down the corresponding object in the derived category. So I take the cochains with values in those script phi gammas. I get the Iwasawa cohomology things. Here for T, here for the same thing with compact supports. Well, I haven't defined them, but you can guess what I mean by this. For T star 1, I have to apply involution. I have to shift by 3. Here I have the same thing for the discrete module. In other words, here I get the cohomology over F infinity for the discrete module. Here I have the same thing with compact supports. For A star 1, again with the involution shifted by 3, and then I get the same diagram, but now with the functors for lambda modules rather for complexes. So here I have phi L, here I have script DL, the Grothendieck dual, here the Pontryagin dual, here phi of L. And so these functors take each complex here to the corresponding complex there. How does one prove that? Well, again, the commutator with phi of L is automatic, and the statement about the diagonal arrows is just a projective limit of the statements at finite levels, which are just the Poitou duality over F alpha. So this also proves the isomorphism for the horizontal arrow, which is really the interesting one, because what does one get from that? So if you are so these are exact isomorphisms in the derived category. Now if you want to pass to cohomology, you have to write down some hypercohomology spectral sequence. So what's the spectral sequence? So hypercohomology spectral sequence for what? For this functor, for the Grothendieck dual applied to, say, this Iwasawa complex with compact supports of T star 1 with involution shifted by 3, the spectral sequence becomes following object E2ij. So here we get xi lambda. Yeah, so now we have to take the derived functors. So the derived functor of this R home is xi. Here we have to take h3 minus j c Iwasawa of of this T star 1 to lambda, and this converges to hi plus j Iwasawa of T. And by using the diagonal arrows, this is naturally just the Pontryagin dual of the corresponding cohomology of the discrete module. So using this formulation, with this term, this spectral sequence was written down by Janssen some years ago, unpublished, but now this is really an immediate, just an automatic consequence of this. So let me finish today's lecture just by remarking that, of course, spectral sequence is not so good because you get all kinds of lambda modules, and in this spectral sequence, the modules for I greater than 1 are all pseudonull. So if you suppress pseudonull modules, you get some nice structure theory, but only up to pseudonull modules, because otherwise you get all kinds of garbage theory. But in the derived category, you get an exact isomorphism, so that's much better. Okay, thank you.